Hey guys, Mr. P. In this video we're going to talk about the atomic structure and how atomic structure leads to the nature of matter. So the first thing we need to do when talking about atomic structure is talk about the basic anatomy of an atom. It doesn't matter what element we're talking about, all atoms are structured the same way. Atoms are made of three different subatomic particles. And those subatomic particles include the proton, neutron, and electrons. The protons are going to have a positive charge, the electrons are going to have a negative charge, and the neutrons are going to be neutral. The protons and neutrons are going to be kept in a particular region of the atom called the nucleus, and so therefore the nucleus is going to have a net positive charge because it contains the protons, which again have the positive charge. And because the nucleus contains the protons and neutrons, it's going to contain virtually all of the mass. Electrons also have mass, but they are incredibly small compared to the proton and neutrons, and so their mass is kind of said to be negligible. The electrons are going to be kept in these electron orbitals, which are surrounding the nuclei of these particular atoms, and are going to be in charge of bonding, both ionic and covalent bonding, which we'll talk about later in this video. The protons are going to give rise to the physical properties of the atom and therefore the physical properties of the element itself. Physical properties are the properties that each of the elements contain. And so when we look at that, we can look at a periodic table. The periodic table is broken into different categories. You have different metals and metalloids, you have different noble gases, and some other transitional elements that are structured certain ways and have physical properties that kind of resemble each other. The physical properties are determined by the protons. We've already said that. And so physically having one proton in the nucleus is going to give rise to the physical properties of hydrogen. When you look at hydrogen, you'll notice that there is an atomic number of 1. You also have an atomic weight or an atomic mass. In this case, it is also 1. Hydrogen has a single proton in its nucleus. It also has a single electron in the first orbital around that nucleus. And so the fact that hydrogen has one proton dictates the physical properties of hydrogen. And hydrogen is very flammable. Hydrogen is a gas. The fact that it's a flammable gas is dictated because it has a single proton in its nucleus. Helium, on the other side, has 2 protons and 2 electrons, which give rise to that atomic mass of 4. 2 protons would have 2 mass units, and 2 neutrons would have 2 mass units, and so it would equate to an atomic mass of 4. Now, this is biology. We're not going to get too specific into the trends of the periodic table or memorize or ask you to memorize different elements, but I wanted you to be aware of the fact that there are elements. They are broken down into groups. Those groups are identified by the table, and when looking at the table, you can come up with trends based on the physical properties of the element. It's just important for you to note that the physical properties are determined exclusively by the number of protons in the nucleus. Isotopes of carbon. So we said in the first slide that a particular atom has protons and neutrons in the nucleus. We also said that there are electrons in orbitals that surround the nucleus. Those electrons have negative charges. So each one of these electrons would carry a negative charge. Each one of these protons would carry a positive charge. And each one of the neutrons would carry a neutral charge. Carbon-12 is the standard or the normal, quote-unquote normal, version of carbon. Carbon, if you looked at the periodic table, would be 6. And would have an atomic mass of 12. Well, carbon-12 is referring to the mass, and so if carbon has a mass of 12, carbon would have 6 protons, which gives it the atomic number of 6, and it also has the 6 neutrons, which gives it a total mass of 12. Carbon-12 would be the normal version of carbon, but there are other versions of carbon, carbon-13 and carbon-14. Carbon-13 and carbon-14 are considered isotopes. What are isotopes? Isotopes are the same element and therefore the same number of protons but a different number of neutrons. And you can see that carbon-13 contains 6 protons just like the carbon-12 did, but it has 7 neutrons instead of the 6 neutrons that the standard version of carbon had. And so therefore carbon-13 would be an isotope of carbon. Carbon-14, again, is an isotope of carbon. It still has 6 protons, so it still behaves like carbon. It's still called carbon. It has 6 protons, but in this case, it has 8 neutrons, which again is more than it should have. It should have 6, but it has 8. And so that is an addition of 2 neutrons, which again is an isotope of carbon. It is important to note that isotopes have the same physical properties because they have the same number of protons, and it's also important to note that it is in fact the exact same element. So isotopes are the same element. So carbon-12 is carbon, but carbon-13 and carbon-14 are isotopes. It is important to note that, by definition, isotopes are atoms of the same element that differ in the number of neutrons they contain as identified, and it's important to note that the total number of protons and neutrons in the nucleus of an atom is called its mass number, and it's really important to note that isotopes are radioactive. What does it mean to be radioactive? Radioactive is when the nuclei are unstable because they have more neutrons than they should, and because they're unstable, they break down at a constant rate. It's called a half-life, and the radiation from the isotopes can be used to date rocks and fossils. They can be used to kill bacteria that cause food spoilage and can be used to detect cancer. The fact that these isotopes, which are naturally occurring, have specific half-lives and break down at a constant rate, once we identify the rate, we can actually identify the age of these fossils and rocks and can use the rate of decay in order to predict or date specific structures that contain these isotopes. So what are some of the applications of isotopes? Again, we just talked about carbon-14, which is an isotope of carbon, can be used to date rocks and fossils based on the rate of decay. If we look at these fossils and there is a certain percentage of the carbon-14 left, and we know roughly how much carbon-14 was there when the organism was alive, then we can do some math in order to determine how old the specimen is. We can use certain isotopes to detect cancer. Because isotopes are radioactive, we can use certain imaging techniques in order to identify where areas in the body might be that exhibit this particular radioactive signature. We can use those to detect cancer. And we can use different radioactive isotopes of iodine to scan the thyroid, because when the radioactive version or the isotope version of iodine is injected into patients, it will congregate in the thyroid, and so it will cause the thyroid to glow, and we can look at specific sizing of the thyroid, and we can make sure it's the proper size. Chemical compounds. So what is a compound? We've already talked about elements. Elements are pure substances that are made up of exclusively one type of atom. So a gold substance, or gold as an element, is made up exclusively of gold atoms. Carbon is made up exclusively of carbon atoms. Helium is made up of exclusively helium atoms. But when we talk about carbon or chemical compounds, a chemical compound is a substance formed by the chemical combination of 2 or more elements in definite proportions. H2O is an example of a compound because it is going to contain, every molecule or every compound of water is going to contain 2 atoms of hydrogen and 1 atom of oxygen. Glucose is the same thing. Glucose has a chemical equation of C6H12O6, so you can see that it is a compound made up of carbon, hydrogen, and oxygen atoms. The physical and chemical properties of a compound are usually very different from those of the elements from which it is formed. If we look at water, water is a perfect example. Hydrogen and oxygen are both gases when in the normal element state, but when you put these 2 gases together, it creates a liquid chemical compound made up of the atoms that were gas at their pure state. Glucose is the same way. Again, hydrogen and oxygen are gas in their pure state. Carbon is kind of a really dark black type element, but when you put this together with the 2 gases, it creates chemical compounds that can actually be seen as like white crystalline structures, like you see when you typically see table sugar. When talking about chemical bonding, there are 2 main forms of chemical bonds we want to talk about. There are ionic bonds. Ionic bonds are formed when 1 or more electrons are transferred from one atom to another. Okay, keyword transferred. And covalent bonds are a really strong bond that are formed when 1 or more electrons are shared. Again, keyword shared. So if we are sharing electrons, it's going to be a covalent bond. When we're transferring the electrons, it's going to be an ionic bond. So what are these bonds in more detail? An ionic bond is just like we said, it's a bond that is formed by ions. So what are ions? Ions are atoms that have a net positive or a net negative charge because they have either an extra electron or they are missing an electron. So a specific example of an ionic bond is when a sodium atom and a chlorine atom come together. Because the sodium atom has a single electron, a lone electron in its outer energy shelf, it wants to discard the electron because it will then fill its outsidemost energy orbital or its outsidemost electron orbital by getting rid of this electron. When it gets rid of the electron, it becomes a positive ion, which is called a cation, because it has one extra proton in its nucleus than it does electrons in its outer energy orbitals. And so because it's a plus one proton, it has a positive charge. Chlorine atom is going to accept the one or single electron from sodium because it is missing one electron. You'll notice that the outer energy levels or the outer energy orbital is completely filled except for one spot. And so it will gladly accept the electron to fill its outer energy level. And when it accepts that electron, it becomes negative because it now has one extra electron than it does proton in the nucleus. Because it has one extra electron, which carries a negative charge, it would be considered an anion and therefore would be a negative charge. Now, the ionic bond forms between the positively charged ion and the negatively charged ion, and so you can think of it like magnets. Opposites attract, and so when you have a positively charged atom and a negatively charged atom, they're actually going to cause the two to kind of act like magnets and kind of attract to one another in order to form this sodium chloride NaCl compound, which you've probably heard is salt. That is an ionic bond. When we compare that directly to a covalent bond, the covalent bond in this case would be water. So we have two hydrogen atoms. These hydrogen atoms have a single proton in their nucleus. They have a single electron in their outer energy level. They each want one additional electron in order to be full. Oxygen has two electron spots that are open, and so oxygen simultaneously wants to fill its outer energy level. And so water and hydrogen can form covalent bonds where the hydrogen is sharing its electron with the oxygen and the oxygen is sharing its electron with the hydrogen. And by doing that, it allows hydrogen to fill its outer energy shell with 2, and it allows the oxygen to fill its outer energy shell with 8. Because they are physically sharing electrons, you can think of them as being locked in place, and therefore creates a very strong bond compared to the ionic bond, which is less strong, but still decent in terms of a bonding strength. Two other types of interactions that can happen as a result of electrons and bonding would be van der Waals forces and hydrogen bonding. The next video is going to be all about water, and I'm going to talk about hydrogen bonding in detail. But for now, hydrogen bonding is a kind of weak bond or a weak interaction between hydrogens and a partially negative charge on, for example, the oxygen side of a water molecules. It creates these kind of weak interactions where water molecules can kind of stick to each other. It gives rise to the physical properties of water. Again, we're going to talk about that in the next video. Van der Waals forces are going to be the forces that allow lizards to use their real big sticky toe pads to stick to glass, because there is a physical attraction between a negatively charged surface and a positively charged surface. Again, more of just an interaction or an attraction between opposite charges more than a physical bond, but it's important to note that that exists. That's all for this video. If you learned something, give it a thumbs up, subscribe to the channel. See you in class.